Hello class, welcome to today's lesson which is 5.7 Average and Instantaneous Rates of Change. This is my redoing of this class because with groups 1 and 2 I have already shown this one, but I don't think it was a very good class, so I had to redo it. And what I'm gonna do is I'm gonna see these two concepts, average and instantaneous, on the other hand, into separate classes. So this is gonna be the first part, and we will only talk about average rates of change. I believe it's much better if we partition this class into two so that you understand the concepts very well. I believe the last class was not very well because I tried to cram everything in a single class and it was a failure. Okay, so let's start. So let's start with the definition of average rate of change. And the definition is the following. It's this: if a variable y is a function of a variable x, which is represented in this way, as you know by now, y is a function of x. In other words, y depends on x. Then we can define the average rate of change of y with respect to x over an interval delta x is defined as the following: delta y over delta x, which is equal to the following: the final value of the variable y minus the initial y over the final x minus the initial x. So first, let me explain to you what this symbol means. The symbol, this little triangle here, this is a Greek letter, and it's called delta. I believe you know it by now. You should know it, delta. And the way this letter is used in mathematics is in order to express a change. For example, let's suppose that you have a little kid, and this kid over the span of I don't know, let's say 3 years, he grows from an initial height, okay, to a final height. If you want to express this change in the height, okay, because that's a quantity that is changing, you can express that change as well in the following way: delta h. Okay, you can read this as the change in the height. That's how you can read it. And by definition, delta h, or delta any variable, by definition is the final value of the variable, in this case the final height, minus the initial value of such variable, which in this case is the initial height. But it's the same for any other variable. I don't know, if you have a bank account and you have a balance, then you may talk about your delta B, delta of balance, and that's going to be your final balance minus your initial balance. Okay, if you want to talk about I don't know, losing or gaining weight, then you can talk about your change in weight, and that's going to be your final weight minus your initial weight. Okay, and these changes can be either positive or negative depending on the relative values of these two, depending on the values of these two, right? The final and the initial values. For example, when you talk about weight, about a change in weight, if you gained weight, let's suppose that's the first case. If you gained weight, that's because your final weight is going to be more than the initial weight. Let's suppose that your final weight is 80 and your initial weight is 75. Then you gained 5. The change in weight is 5. Okay, you had a rise in your weight. But it can also be negative, right? And what that means is a loss of weight. The change in weight, if let's suppose it goes the other way around, now you're gonna lose those kilograms, those extra kilograms. So now what is your final weight? It's gonna be 75, and your initial weight was 80, and therefore the change will be minus 5. The change in weight is minus 5, which means or represents a loss of weight. You see, so the deltas of variables can be either positive or negative depending on the relative values of these two variables. Okay, so that's what it means. That's what this symbol means. And it's written in here, okay? It's like I said, it's YF minus YI. That's what this symbol means. And over XF minus XI. And when I say F and I mean final and initial. Okay, so that's the formal definition of rate, an average rate of change. By the way, why am I writing this in here? Okay, and what does this symbol mean? This symbol, which is, it's mathematical symbology very similar to the 3 points that teacher Hugo taught you. This is therefore, and this symbol means equivalent. Equivalent. So basically what I'm trying to tell you is that this frame, this rectangle, what is inside is equivalent to this, okay? Why? Because as I said, y is a function of x, and therefore we can talk about the change not in y, but the change in the function over the change in the x variable, and that's going to be equal to this, because yf is equal, if we know that y is a function of x, then yf, or the final value of y, will be the function evaluated in the final value of x. You see, that's why I wrote this instead of this. So they are equivalent statements, and I do this because you need to be acquainted with these different types of representations of the same thing. Different symbology doesn't mean that you have different mathematical objects. Okay, so let's move on. That's the formal definition, because you need to hear it, you need to listen to it, you need to read it. But actually, the conceptual understanding of this concept is very simple. You're gonna see why in a moment. And let me also tell you about the reason why we need to add the word average to this definition. You see it right there. The average rate of change. The average. I'm not saying just the rate of change. No, I need to add average. The average rate of change. And that word is extremely important in this definition. When do we use the word average? We use it whenever a quantity changes, right? For example, suppose that you go from your home to CDEP over a straight line, and there are no obstacles in between, okay? There are no speed bumps or traffic lights or any other cars. So you live along a straight line with CDEP, and there's a road over there. And if there is nothing that impedes your passing through, then basically you can get into your car and travel at a constant velocity, right? Like you can step on the gas pedal and travel, let's say at 90 kilometers per hour, and get to CDEP at that constant velocity. So when somebody asks you, okay, what was your velocity throughout the journey? You can just say, my velocity was 90 kilometers per hour. And that is perfectly okay. And what that means is that you kept that velocity constant throughout the journey, 90 kilometers per hour. Simplest case scenario, when this thing is not changing, when the quantity of interest is not changing. But the other more realistic scenario number 2, is when in fact you have, like we know, I don't know. Let's suppose you have some speed bumps at the beginning, and then you have traffic lights, and then you have another cars, you have traffic, etc. Okay, so all of these things are gonna impede your passing through, and they're gonna make you change the velocity. You have to slow down when passing through a speed bump. You have to stop completely on a red light, and the traffic is gonna slow you down, etc. And then you're gonna speed up, etc. So basically, your velocity is changing throughout this journey. It's changing constantly. Sometimes you can reach 100 kilometers per hour. Sometimes you're gonna stop completely at the traffic lights, etc. So when you arrive at CDEP and somebody asks you, what was your velocity throughout this journey? You cannot answer something like this. You cannot say, Well, my velocity was 90 kilometers per hour or 80 kilometers per hour. That would be false because that's not the velocity you kept throughout the whole motion. Okay, what you should add in a case like this, which is the more realistic case, you need to add the word average. My average velocity was, I don't know, let's say 70 kilometers per hour. That was your average velocity over the whole motion. Does that mean that you always traveled at this velocity? No, 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 no. It means that you went over it sometimes, below it sometimes, even zero, etc. So that's what the word average means in mathematics. I know that you know it, but I need to make sure that you understand really the meaning of this, and you're gonna understand why we need to add this word to this definition in a moment. Okay, so that is the first thing. I'm gonna pause for a moment and I'm gonna come back with more explanation. Okay, now we're gonna analyze these two graphs, this one and this one. You're gonna see the next one in a moment. And basically what we want to do is you're gonna learn how to get the average rates of change and what they mean by means of examples. So I'm gonna give you three examples in here. This is the function. It's f of x equals to x. Remember that we usually say, or we write this, that the variable y is a function of x, and we talk about them indistinctively, okay? Y and the function f are the same. That's what this means. Y is equal to the function of x. Okay, so the first task is telling me find this, which is the average rate of change. You have to read this as the average rate of change of y with respect to x. So find the average rate of change of y with respect to x, or just the average rate of change, that is enough, over an interval delta x where the initial x is 1 and the final x is 2. So what do? I stick to my definition of the average rate of change over an interval, which is this, the change in y over the change in x, or just delta y over delta x, the final value of y minus the initial value in y, the final value in y minus the initial value in y over xf minus xi. Sometimes saying xf and xi is much more comfortable, right? You say less words. Okay, so let me spot these points. Okay, what is the interval that I'm talking about? It's when x moves from 1 to 2, from here to here. So basically the points that I'm talking about are these two guys. These 2 points are the points of interest because x is moving from here to here, and as x does so, the y is moving from here to here. Can you see? Like, let me do this. You see, for 1, this is the value of for x equals 1, this is the value of y. For x equals 2, this is the value of y. And so basically what we're doing is, this is your delta x, this is your change in x, this is your change in y. Okay, so let's compute this. What is my yf? It's gonna be 4 minus my initial value in y, which is 2, over xf minus xi, which is 2 minus 1. And then we have 2 over 1, which is 2. There you go. So the average rate of change of y with respect to x over this interval from 1 to 2 is equal to 2. That's it. That's the result. Now, what it means? Now that we have calculated it, what does that mean? The way we can interpret this number, guys, the average rate of change of y with respect to x, is this. Over this interval, as x moves from 1 to 2, your variable y changes by, for every unit that x runs horizontally, your y changes by 2 units. Okay, it changes twice as much. That's what it means. That's what this word, the word rate, means. Okay, it's like how much does this variable change with respect to this one, for every single unit that this one advances. Okay, how many units does y advance? That's all it means. It's a very simple idea. Okay, so that's the first task. Let's go with the second one. Let me erase all of this first. Okay, what about the second one? Find the same thing, the rate of change of y with respect to x over an interval delta x when xi equals 2 and xf equals 3. So what are my points of interest? From 2 to 3, therefore from here to here. So basically, this is my change in x, and this is my change in the variable y. Okay, I'm not gonna do the 4 lines because I don't want to clutter the diagram. Okay, so let's stick to the definition and let's compute such quantity. It's gonna be yf minus yi over xf minus xi. And what is my yf? In this case is 6. You see, this is the final value of y, and the initial value is 4. And in x, we have the final value 3 and the initial equal to 2. So we have this. So 6 minus 4 is 2, 3 minus 2 is 1, and we have one more time 2. Okay, which makes sense. Why? Because this is a linear function, and the principal feature of a linear function is that the rate of change of the variable y is always the same uh, with respect to x. Okay, it's always the same. It's proportional. That's the principal feature that you have been learning about these types of linear functions. So in this case, it represents the same thing. For every over this interval, for every little bit that the x advances, I'm gonna represent that in this way. Like imagine a little person in there walking all this much. Okay, if that person walked that much to the right, how much did he walk vertically? Well, twice as much. 1, 2. Can you see? Okay. Well, maybe not. Maybe try not to imagine the person going from here to here. Try to imagine this person as if walking up a hill, like from here to here. As he walks up the hill in this inclined fashion, what you can understand is that he's walking a little bit to the right and a little bit upwards. And for every little bit that he walks to the right, for every little bit, he's walking two of those little bits upwards. That's what these two means. That's what the rate of change means. That's the idea. That's the concept. You have to understand the concept. The concept. And finally, number 3, do the same thing. Find the average rate of change over delta x, where xi is now 0.5. So that's a decimal value. No problem with that. It's perfectly okay. And the final value of x is 1. So let's do that one. So now my points of interest are this and this, as you can see, because this is 0.5 and this is 1. So now my delta x is this much and my delta y is this much. And let's see what happens when I don't even walk like a whole unit like before. You see, it was a whole unit in the x-axis. Let's see what happens now. Are we gonna get the same? As you may be guessing, yes, we're gonna get exactly the same. So I'm gonna do it directly now. What is my final value in y? It's gonna be 2 minus the initial value in y, which is 1, over my final value in x, which is 1, minus my initial value in x, which is 0.5, Okay, let's calculate this. 2 minus 1 is 2. 1 minus 0.5 is 0.5. We make this division and we will get one more time 2. Because, I repeat, for a linear function, the rate of change, or more specifically, the average rate of change, will be always the same. It will never change. Okay, so I hope you have understood that concept, guys. The average rate of change, okay, of y with respect to x, at least in this linear function, which is the simplest type. Okay, and if you notice, guys, for this function in particular, which is the simplest type that we know, the word average is kind of like unnecessary, okay? Because in fact, the rate of change is always the same. You see, it's 2, 2, 2, whatever 2 points you choose. If I ask you what is the average rate of change between these 2 points, well, you get the delta x, then you get the delta y, and you will find that it's always the same, 2 in this case. So the word average is kind of like overkill, so to speak. You may just as well just say what is the rate of change of y with respect to x when you talk about a linear function. But that's the problem. The problem is that most functions are not like this one, and you will see the utility, or not the utility, the need to add the word average when we do the same thing for other type of more complicated functions, like we will see in a moment. Okay, now in order to conclude this lesson, guys, we're gonna analyze now a non-linear function. In this case, f of x equals 1/2 of x squared. Here is the graph. And we're going to do something very similar. We're going to calculate average rates of change of y with respect to x over certain intervals given for this graph. And then we're going to interpret what they mean. So let's do that first. So find the average rate of change over delta x, where xi is 0 and xf is 2. So I'm going now from here to here. Okay, what is my delta x? Is this much. What is my delta y? It's this much. Okay, and you can go like this, delta y over delta x. You don't have to do you don't have to do this exactly, but this thing that I just wrote, but that's technically the definition of it. So as we know, the delta y is 2, so I can just write it down immediately, and delta x is also 2, and so we have 1. There you go, completed. So the rate of change, the average rate of change of y with respect to x over this interval, same thing, from 0 to 2, right there. Over this interval is 1. Okay, we're gonna interpret this number in a moment. Now let's do the same for this one, yellow. Find the average rate of change over delta x, where the initial value of x is 2 and the final value of x is 4. Okay, so let's write this down. Now we're gonna go from 2 to 4. So this is gonna be now my point of interest here, and the final point of interest will be this one, because this is 4. We're gonna go from 2 to 4. Let me erase the white marks. So now this is my change in x. This is my change in y. Of this. And as we can see, the change in y goes from 2 to 8. So we can calculate it immediately, and it's going to be 6. You see, you can do it graphically. It's very simple. And the delta x goes from 2 to 4, which is now 2, right? Because it's 4 minus the 2, it's going to be 2. and therefore the average rate of change over this interval is 3. Okay, and let me stop right here and let's analyze these two numbers, this number and this number. What do they mean? Okay, so what this means is the following, guys. And now we're gonna have to use or now we're gonna see the need to use the word average when we talk about these types of functions, because what this number means when we say that the average rate of change over this interval delta x from 0 to 2, when I say that the average rate of change over this interval is 1, what I'm saying is that on average, as the person travels now, going back to that same example of a person kind of like traveling up a hill. In this case, the hill has this shape. That's okay. That's we can imagine that a hill has this shape. On average, as he walks, well, let me use a she now. As she walks a little bit on the x-axis, okay, to the right, on average, she's also gonna walk one little bit upwards, okay? As she displaces to the right 1 unit, she's gonna displace also upwards 1 unit. Is that the same all throughout this interval? No, 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 no. As you can see, at the very beginning of this interval from 0 to 2, at the very beginning, she's walking more. Uh, she's having greater strides on the x-axis than on the y. Can you see? As she goes from 0 to 1, look at how much the advancement or the progress in x she takes, and look at how little it is on the y-axis. Can you see? And now suppose that she arrives at this point. Now she's right there. Now from 1 to 2, as she walks another unit, look how much she raised upwards, all this much. So in both cases, in this case and in this case, she walked 1 unit to the right, but we can see that the rise in height is different. This is smaller than this one. So you see, even within this interval, within delta x, the rate of change of the height with respect to the horizontal distance changes inside. So we cannot say that all the time as she walks 1 unit to the right, she's gonna walk or she's gonna ascend 1 unit in height. Okay, what we can say is that on average, as she walks 1 unit to the right, she's gonna ascend 1 unit in height upwards. On average. That's the reason for adding this word. You see? That's the reason for it. Okay. And the same thing for the other, right? As she walks from 2 to 4, okay, from in this over this interval from 2 to 4, or in other words, as she travels, as she ascends this mountain from this point to this point, on average, as she does so, on average, she walks 3 units upwards, or she ascends 3 units upwards per unit traveled to the right. That's what it means also, you see. But same thing, it's not the same all throughout this interval, okay? It's not the same. And if you want to be convinced, let's do this one. Look, find the average rate of change over delta x, where the initial value of x is 2 and the final x is 3. So this little interval is actually inside this interval. It's going to go from 2 to 3. Can you see? This interval lays inside this interval. And let's see what happens if we calculate that. Let me erase this. So my initial point is 2. My final point is in x, is 3. Okay, so these are my points of interest. This is my change in x. This is my change in y. Okay, so if I want to calculate the rate of change of y with respect to x, I have to calculate my delta y, which is 2 and maybe 0.5. I don't know if that's true, but let's do it. 2.5, more or less, okay? Remember, more or less. And the delta x is 1 unit. So this is going to be 2.5. There you go. This is the average rate of change, approximately, over this little interval, which is inside this interval. You see? So you can see that even within an interval of which you have already calculated the average rate of change. For this one, we went from here to here and from here to here. And we said that the average rate of change is 3. Well, if I calculate now, if I use even a tinier interval, this interval from 2 to 3, which is this one in here, and this is the corresponding value of y, delta y, then you can see that it's 2.5. The average rate of change in y over x with respect to x is 2.5. You see? So the rate of change in these types of functions, guys, when you are managing nonlinear functions, it's always changing. It sounds weird. It sounds weird to say that the average rate of change changes itself. You see, it's kind of weird that, but it's how it works. It's how it works, and that is the reason for having the word average. Okay, that you need to understand that very very well. Okay, guys. I think that's enough for today. Like I said, I want to give this in 2 parts, probably even 3, because I want you to understand the concepts very well, with care and with a lot of time. Okay, so tell me if you have questions, and if not, you can start working on the exercise from the workbook. Thank you, guys.